There is a person standing 1 meter away in front of you. Please move forward slowly.
Greetings to all who are watching. My name is Arnav Sharma, and my innovation aims to leverage artificial intelligence technology and give blind people back their sense of independence. There is a reported population of 70 million visually challenged people in India alone, out of which 15 million are blind. Despite the recent breakthroughs in the fields of artificial intelligence and other such technologies, blind people still have to trade their sense of individuality and independence simply to get about through their day. This significant problem inspired me to work on a device that will give blind people the same guidance as a real person, but at the same time helping them retain their own sense of independence. Introducing Ivory Cane, a novel method to revolutionize the way that blind people navigate their surroundings. Ivory Cane does so with the help of various cameras and various sensors to detect the environment of the user and give back live real-time feedback in the form of guidance. To do so, I divided the development of the device into three different phases, namely the eye, the brain, and the mouth. The first phase of the object detection loop takes its inputs from three main sources, which is a 3D camera, meaning a camera with depth detection, and a TF Luna Micro LiDAR sensor, which gives us a range of around 8 meters, and third, an ultrasonic sensor as a fail-safe in case the first two fail to detect something in the immediate vicinity of the user that could be a danger. Using a very simple mathematical formula, I'm also using the LiDAR sensor to calculate the speed of the user along with the speed of dynamic objects around them. The brain of the device is a microcomputer. The Raspberry Pi runs semi-custom and custom algorithms with pre-trained AI models. To be specific, these are the algorithms that I'm using. It was important to find a good balance between the time that it takes to detect along with the accuracy. Euro v3 and SSD are a good trade-off for this. The cloud directories of GoogleNet are sufficiently trained for object recognition as well. Reinforcement pattern training is not something that I've implemented as of yet due to the limited resources at my hand, but something that I do plan on doing in future with this device. I plan on using DQN with TensorFlow along with Keras for reinforcement learning. The third and the final phase of the loop consists of the mouth, which is basically a pre-trained language model to convert the guidance into humane and intricate sentences. Currently, I'm using Distilbert, which has over 40 million pre-trained parameters. And in the future, this also keeps open the possibility of integrating character recognition, which I plan on doing. After a humane and intricate sentence is computed, then the statement or the guidance is sent into the ears of the user through a wire. For example, out of the many parameters that I had set, here are two decision trees chosen at random to give you an insight at the back end of the software. The first decision tree outlines the process of detecting objects, generating textual descriptions, and processing the text with BERT. Coming to the novelty of the device. This device is user-friendly, which is quite literal in the sense that reinforcement learning will allow the device to learn from the user's patterns and become more and more familiar with their day-to-day goings. Moreover, the indoor testing accuracy of the most recent prototype, according to WHO guidelines, is already enough to be implemented as a scalable prototype. The project holds major potential for scaling to a wider audience, with its manufacturing price cost being 360 USD. We can also make use of the government schemes and tie up with the government for mass manufacturing to reach the rural areas as well. During the testing phase, I was fortunate enough to get to work with an MSVI individual whose feedbacks were very valuable to us. The two major concerns that came up were the proximal danger, meaning any undetected object that could have somehow made it very close to the user, such as dynamic objects like moving vehicles. And the second concern was the weight, which would have tired the hands of the user if he were to use the cane for the whole day or hold the cane for the whole day. This particular user wanted to be around more humans. So for that, we had to come up with a very sensitive and intricate decision-making process. I came up with this decision tree to reflect a more integrating advanced sensor fusion and personalized modes based on user preference. Now to deal with the second problem, which was the weight, we changed the previous design and we added some straps beneath it, now making the device semi-wearable. We also added some extractable or retractable points at the cane. In case the user gets tired, he can retract the cane